Next section is section 9.3. You'll notice that we've made a little bit of a jump. We're going to be covering chapter 8, this one section from chapter 9, and then a couple sections from chapter 10, just in order to do all of the intervals together. So in the past couple of sections, we've done intervals for one proportion. We've done intervals for one mean, whether we either knew the population deviation or we did not. And section 9.3 goes very well with 8.3 in that you're still talking about an interval for a mean, just with a slight change, a slight tweak of now looking at intervals for matched pair data. So to do kind of a throwback to first semester stuff, here was a warm-up problem. Acumen Medicine is conducting an experiment to test a new vaccine. They've selected 1,000 volunteers, 500 men, 500 women. Describe how you could do this either as completely randomized, block, or matched pairs. And we discussed this a little bit as a class. Completely randomized would be where you just took all 1,000 people, put their names in a hat, and drew out the first 500 to get the new vaccine versus maybe a placebo vaccine or nothing for the other 500 people. So regardless of age, regardless of gender, that would be completely randomized. Block would be, for instance, where you could separate men versus women if you think they're going to have different responses to this vaccine. Or instead of men versus women, you could block by age. For instance, young people versus middle-aged people versus older people, if you thought that would have the most effect on how they would respond to this vaccine. Any of those options could be considered block design. Matched pairs would either be where you took everyone in the study and randomly assigned them one of the treatments, so by flip of a coin or a random number generator or something like that, and see how well they did avoiding a cold this first year, and then the next year they would get the other treatment and then see how they fared in terms of how likely they were to get a cold or not. Or if you matched people up that were as similar as possible, so men with men, women with women, of the same, both of which of the same age group, so two 20-year-old males with similar health histories, for instance, would be paired up with a flip of a coin. One would get the first treatment, one would get the other treatment, and then because they were as similar as possible from the beginning, we could track progress throughout that the year, however long this vaccine would last, and see how often or who got the colds and how often each of those pairs got sick. Okay, so here are some examples and some specifications for what something needs to be a paired experiment, and therefore we need a paired t interval or matched pairs interval. They need to be dependent samples, meaning that if you have the response to one treatment would depend on the response to the other treatment, it would be when you're reading the examples, the case where you have different results within the same population. So, for example, if I have the same similar survey questions but worded in two different ways to determine whether their opinion would remain the same based on the wording, that would be matched pairs. And if I have, and we'll talk about this example in just a minute, people take some kind of depression test or rubric with versus without caffeine. That would be matched pairs. So either matched two people who are very similar in terms of history of depression together, or do the same people just one day with, one day without caffeine, and measure how it feels, how their moods would add up on the depression analysis. Okay, pre-test and post-test scores for a group of students. So the same students were tested before and after a lesson of some kind to see how the lesson impacted their understanding of the material. Another example our book gives is number of disruptive behaviors on moon days, meaning where there was a full moon or nearly full moon out versus on non-moon days. Here is the just intro to the paired t-interval part. It will be used to estimate the average difference in batch pairs experiments. I'm still going to be applying the same t procedures as before, so the same conditions, the same calculations for the most part, except I'll be doing them on the differences. So x bar will be the x bar of the differences. I will take each of the pairs of data, subtract, find the differences of them, and then I'm going to find the x bar of the difference. I'm going to find the deviation of the difference. I'm going to find the t star based on the degrees of freedom with a number of pairs minus 1, not the number, just how many numbers do I have, but how many pairs did I have minus 1. And then same thing with my sample size. It's not all how many numbers do I have total, it's how many pairs of numbers do I have that I calculated in differences. So here's the fleshed out version of the caffeine dependence. So I'm going to estimate with 90% confidence mu, which is the true average difference, or the true mean difference in depression scores for with and without caffeine. Because I'm going to be finding differences, I do need to state which way I'm going to subtract. I personally like to subtract in a way where I think I'm most likely to get positive numbers. I like positive numbers better than negatives. So if I think that depression scores are going to be higher without caffeine, meaning with the placebo, then I'm going to put the placebo first. So the mu difference is what I'm estimating for, and I'm going to say that is equal to placebo minus the caffeinated scores. The plan is to be a paired t-interval. If you just call it a one sample t-interval or even just t-interval, that would be considered fine in terms of naming the test. The order of treatments in this case, since it was 11 people who underwent both treatments, the order of treatments was randomly assigned. That is important. So not everyone had caffeine first. About half would get caffeine first, half would be on the placebo first. I would put each of these lists of numbers into L1 and L2, find the difference in L3. So what I did was put maybe the placebo scores in L1, the depression scores for caffeine in L2, and then do the difference in L3, and then I made a normal probability plot of just L3. So I have some concern with such a small sample that it is not exactly linear. There's a little bit of wave out to the side. So I would say normal condition not met, or proceed with caution. The sample can be considered independent as long as the different subjects do not influence one another. Okay, so if someone is more depressed with caffeine, they're going to be more likely to be more depressed without caffeine. That's not the independence I'm worried about. I'm worried about in between each subject. So subject 1 doesn't have any effect on subject 2's depression score, in other words. Okay, on the do step, there is my x bar, my average for the difference. So once again, it's not on either one of these, the caffeinated or the non-caffeinated scores. It's on the L3 data. So the average difference is 7.36 in scores. 1.812 is from my t-table, just like last time. So based on, if I have 11 subjects, I would have 10 degrees of freedom with 90% confidence. That's where I got the 1.812. The standard deviation for the difference was 6.92, and then there were 11 pairs of data. Here is my setup for my interval. This is what it looks like on the calculator. T interval is immediately under Z interval in the calculator. And then conclude, I'm 90% confidence that the average, or that the interval between 3.58 and 11.14, which is what I got when I added and subtracted the margin of error, would capture the true average difference in depression scores between patients with and without caffeine. Okay, Here's another example. Also in our book, we have different brands of tires. One filled with just the usual mix of air that would be in a tire pump. One filled with strictly nitrogen. This is what they use in aircrafts. They discovery that's less likely to explode, which is why it's used in aircraft. And researchers are interested in seeing if they would also be less likely to lose tire pressure. So the different brands of tires, there were 2 of each tire. One was randomly assigned air, the other got nitrogen. And then they were all set under the same conditions, outside, exposed to the elements. At the end of the trial period, the air pressure was checked. And the amounts that you're seeing here is how much each tire lost in air pressure over the time period. So subtract air minus nitrogen, if I think that mixed air is going to have a higher rate of tire pressure loss. And we just did this one for additional some practice with doing the calculation. So the book asked us to take a look at what would the interval look like with a couple of outliers. So if you look at the data of the differences, you will see 2 that have extreme amounts of difference between the airs and nitrogen filled tires. So with those, I end up getting an interval between 0.81 and 1.69. If you remove those 2 outlier data points and look at the rest of them, okay, so only 29 instead of 31, you have a smaller average difference, smaller deviation. You have a smaller t-value since my degrees of freedom is less, and you end up getting a more a lower interval in terms of your estimate for how much of a difference in air pressure you would lose in the 2 treatments. Okay, take a look at, just wanted to introduce what it would look like as an AP problem. This is computer printout of information. It's been pretty standard in the recent AP tests that they will give you the difference and the mean and the deviation already calculated for you, so you don't waste time doing that on the test with the raw data. So here is the sample size, how many pairs were provided, the average difference, the standard deviation of the difference, and the standard error, the mean. So I've actually already calculated this part of the margin of error. In order to come up with the confidence interval, I would just have to take negative 2.015 plus or minus the t-value times the 0.336, and that would give me my answer. Go ahead and try the 9.2 problems. Notice I've put in some confidence levels for you to try them with. Do them as intervals, not as the book says, hypothesis tests, and then we'll talk about our answers next time.